So, I want you to imagine something for a second. A computer that doesn't just crunch numbers one by one, but one that explores millions of possibilities all at the same time. We're talking about a machine that runs on physics so weird, even Einstein himself called it spooky. And no, this isn't some far-off sci-fi dream. This is happening now. It's the dawn of the quantum revolution, a totally new era of computation. All right, so here's how we're going to break this down. First, we'll talk about the classical dead end, basically why our current computers are hitting a wall. Then we'll introduce the hero of our story, the qubit. After that, we'll get into quantum secret sauce, the wild physics behind it all. We'll see what the quantum advantage actually means for us, and finally, we'll look at the huge task of building the quantum future. Okay, so first up, the classical dead end. You gotta ask, why do we even need a new kind of computer? You know, it's kind of wild to think about, but that brand new phone in your pocket, or that super fast laptop you just bought, deep down, they're running on principles that were figured out way back in the 1940s. Yeah, they've gotten insanely fast, for sure. But the basic blueprint, well, it's starting to show its age. It's hitting a fundamental wall. And look, this isn't something we can just fix by making a slightly better chip. We're talking about really deep fundamental limits. See, our computers, at their very core, are binary. Everything is a 0 or a 1, on or off. And for the most part, they chew through problems one step at a time. For some really, really hard problems, like say trying to perfectly simulate a new drug molecule, that's just not going to cut it. You'd literally need a computer with more bits than there are atoms in the entire known universe. So yeah, we're basically running out of road. For the last 50 years, we've had this incredible engine driving progress forward, Moore's Law. You've probably heard of it. It's the idea that the number of transistors we can cram onto a chip doubles about every 2 years. That relentless shrinking is what gave us the entire digital world. But that engine is starting to sputter out. We're trying to build things so small now, we're talking about the scale of individual atoms. At that level, the normal rules of physics get weird, and the sheer amount of heat these things generate is becoming a massive, massive problem. So, if the classical computer is hitting its limits, where do we go from here? Well, we have to jump into a whole new world and meet the absolute cornerstone of it. And here it is. Meet the qubit, the quantum bit. This is the heart of the entire revolution. You see, a regular computer bit is simple. It's either a 0 or it's a 1. That's it. But a qubit, it can exist in what's called a superposition, which means it can be both a 0 and a 1 at the exact same time. And that one little difference, well, it changes absolutely everything. Let's use an analogy. A classical bit is like a light switch. It's on or it's off. Simple. A qubit, on the other hand, is more like a dimmer switch. It's not just on or off. It can be any value in between. Its nature is all about probability. Now, here's the crazy part. The moment you actually look at a qubit to measure it, it's forced to pick a side. It collapses into being either a 0 or a 1. The entire magic of quantum computing is about carefully nudging those probabilities so that when it finally collapses, it lands on the answer you're looking for. Just to give you a visual for how much more information a qubit can hold, think of a globe. A classical bit can only be at the North Pole, that's a 1, or the South Pole, that's a 0. Just two options. A qubit, it can be any point on the entire surface of that globe. That's how much richer its state can be. All right, so we've got the qubit. Now let's talk about the two mind-bending quantum effects that give it its superpowers. This is the real secret sauce. First up is superposition, which we've kind of talked about already. The best analogy is a spinning coin, right? While it's spinning in the air before it lands, is it heads or tails? Well, it's kind of both. That's like a qubit. And when you have a bunch of them, the power just explodes. A system with n qubits can explore all 2 to the power of n possibilities simultaneously. That's a level of parallel processing that classical computers, they can't even come close. Okay, but the second ingredient is where things get really, really weird. It's called entanglement. This is, well, it's this deep, mysterious link between 2 or more qubits. Once they're entangled, they act like a single system. If you measure one, you instantly know the state of the other one, even if it's on the other side of the universe. There is just nothing like this in our normal everyday experience. This connection is so bizarre that it famously freaked out Albert Einstein. He was the one who called it spooky action at a distance. He just couldn't wrap his head around it. But here's the thing. Decades of experiments have shown, again and again, that it's 100% real. It's just a fundamental and incredibly powerful feature of how our universe works. Okay, so we have all this spooky, powerful physics. What's the point? What can we actually do with it? That brings us to the quantum advantage. Now, it's really important to understand that quantum advantage doesn't just mean a little bit faster. We're not talking about a 10% speed boost. We're talking about a complete paradigm shift. It means solving problems that even a classical supercomputer the size of Earth couldn't solve in a billion years. It's about making the impossible possible. And this is where it gets really, really exciting. What kind of problems are we talking about? Well, things like designing brand new medicines and materials by simulating molecules with perfect accuracy, or breaking the encryption that protects basically all of our private data online, or solving insane logistical puzzles for shipping and finance to make everything more efficient. We could even build climate models that are vastly more accurate than anything we have today. These are the huge world-changing problems that classical computers are just fundamentally stuck on. All right, let's bring it back down to earth for a minute. This all sounds incredible, but where are we right now? What are the big roadblocks on the way to building this quantum future? So, this journey actually started a while ago. The legendary physicist Richard Feynman first floated the idea way back in 1982. The big, groundbreaking algorithms came out in the 90s, but things got really real in 2019 when Google announced it had achieved quantum supremacy. That's a huge milestone where a quantum computer did a very specific task way faster than any supercomputer could. Right now, today, we're in what's called the NISQ era. That stands for Noisy Intermediate Scale Quantum. Basically, it means we have these machines, they work, but they're small, super sensitive, and make a lot of mistakes. And the challenges are, well, they're huge. The number one enemy is something called decoherence. Qubits are unbelievably fragile. The tiniest bit of heat or even a stray magnetic field can knock them out of their special quantum state and ruin the calculation. This fragility leads to way more errors than you'd ever see in a normal computer. And then there's the sheer scale of it all. Going from the dozens of qubits we have today to the millions we'll need for the big stuff, that is one of the toughest engineering problems humanity has ever faced. But despite all that, the promise is absolutely massive. The real takeaway here isn't just that quantum computers will give us faster answers. It's that they'll let us ask completely new questions, questions we don't even know how to ask yet. They'll open up entirely new ways of seeing the world. So that leaves us with the biggest question of all. What will we ask first?